Welcome to this fourth video lesson on work, energy and power. Today we're going to look at the law of conservation of mechanical energy, which in a very simplified form says the following. In a system, without friction, the mechanical energy of the system is constant. So in essence what this is saying is that if there's no friction to cause energy losses, then the mechanical energy of the system at the start will be the same as the mechanical energy at the end. So if I can state this mathematically, we can say the following, that the mechanical energy is constant. Now we represent a constant with K, and the mechanical energy we know is the potential energy, plus the kinetic energy at a point in the system. So we can say that, well, if we look at the initial situation, if we look at the mechanical energy at the initial situation, and then we look at the mechanical energy at the end, in the final situation, then the potential energy plus the kinetic energy at the end, we can say the final situation will be the same. Now, for that to be true, that means that if you look at the sum of the potential energy and the kinetic energy at, let's say, point A, and you look at the sum of the potential energy and kinetic energy at point B, then they should be equal. So irrespective at which points you're looking at the system, the sum of the kinetic and the potential energy should be the same, because the mechanical energy is kept constant or is conserved. So let's consider an example. A ball of mass 2 kilograms rolls along a frictionless path as shown below. So we observe this system when at point A the ball has already been accelerated to the point where it has a velocity of 2 meters per second. So we start to observe the system here. So it's got a velocity of 2 meters per second, which means that the ball has got a kinetic energy because it's moving. And because the lowest point B is here and A is above B, the gravitational field which acts downwards, and I'm going to represent it with these little dotted lines and arrows, is going to cause A to move downwards toward B. We know this. We know that objects slide down slopes of their own. Now, A is going to have a potential energy because of the fact that it is at a certain height, in this case 5 meters above the lowest point. So at point A, the object, the ball, has both potential and kinetic energy. So let's now go and answer the first question. What is the mechanical energy at A? And so we're going to need to work out what is the potential energy and the kinetic energy. So I'm going to do that here. I would like to work them out separately. So let's start off with the potential energy. So the potential energy at A is going to be the mass of the ball times gravity times the height at A. So the potential energy at A is going to be the mass, which is 2 kilograms. G, because it's on the earth, is 9.8 newtons per kilogram. And when the height is, in this case, at A, the height is 5 meters. We're going to define at point B, which is the lowest point, at the height there is 0 meters. And so therefore this potential energy, the potential energy at B would be 0. This was also, so B would be what we call the zero potential. So now if we substitute 5 in. We go here. We substitute 5 in. This is 5 meters. Then when we work that out, 2 times 5 is 10 times 9,8 is going to give us 98 joules. Now, if we look at the kinetic energy of the object at A, it's going to be a half the mass times the velocity of the object at A squared. So that's going to be a half times 2 kilograms. And the velocity at A, if we look there, we see the velocity of A is 2 meters per second. So we go up here, sorry, should I say down here? So this is going to be 2 meters per second squared. And so what we're going to get is a half times 2 is 1, and 2 squared is 4. So this is going to be 4 joules. So the mechanical energy at A is going to be the sum of the potential and the kinetic energy. So it's always good to put down the general formula to show that you know what you're doing. So potential energy at A is 98 joules, and the kinetic energy at A is 4 joules. So therefore the mechanical energy at A is 102 joules. So that means that the total energy of the ball at A is 102 joules, 98 of which is made due to, or consists of potential energy due to the height of the ball above ground level, and the other 4 joules because of the motion that the ball has. Now, let us now look at question number 2. So number 2 asks us, what is the mechanical energy at B? So what's going to happen is that this ball is going to roll down here and it's going to speed up. Now, because of the fact that the path is frictionless, this automatically implies conservation of mechanical energy. Conservation of mechanical energy. So we can automatically say, if this was 1, that 2, that the mechanical energy at B is going to equal the mechanical energy at A, which is going to be 102 joules because this system is frictionless. Now, in practice, it's virtually impossible to get a frictionless mechanical system. So this is highly theoretical. Now it asks us, what is the kinetic energy at B? So if we look at it conceptually, before we work it out mathematically, at this point, the ball at point A has got kinetic energy because of its velocity and potential energy because of its height. When it gets to the bottom here, its height is 0. So there's no potential energy. The potential energy is 0. Now, if the mechanical energy is the same as the mechanical energy up there, then the mechanical energy at B must therefore surely consist purely of kinetic energy. So if we look at 3, we can say that, well, we're going to work it out now mathematically. The mechanical energy at B is going to equal the potential energy at B plus the kinetic energy at B. But we've just worked out that the mechanical energy is 102 joules. And because the height at B is 0, we know that the mass is 2 kilograms, G is 9,8, but at B, the height is 0. So therefore, the potential energy is 0 joules. That's why we call it the zero potential, plus the kinetic energy at B equals 102 joules. So therefore, EK at B is 102 joules. Now, science and physics and chemistry is not about just getting answers. It's about actually understanding the concepts, understanding the principles behind the mathematics. So what's happened here, and we experienced this, is if we stand at the bottom of a hill and someone on a skateboard is above us further up the hill, and then they push off and they come down toward us, straight toward us, we are not going to stay there, because we know intuitively that by the time they hit us, their speed is going to be way more than when they pushed off at the top. In energetic terms, in terms of energy, we know that the collision is going to be hugely damaging to us, because the potential energy that they have at the top of the hill is now going to be converted into kinetic energy by the time they get to the bottom of the hill, and that kinetic energy is going to do work on us, and in doing so is going to injure us. So all of the kinetic energy has been, all of the potential energy at the top of the hill here, all the potential energy at the top of the hill has been converted into kinetic energy, which has been added to the kinetic energy there, which means it's now all of the mechanical energy is in the form of kinetic energy at the bottom. So let's now move on to the next question. The mechanical energy at sea. Well, there too, that is easy. Because if we go now and we look, we know that the object is moving along a frictionless path. So at every point along this path, it's not going to lose energy. It's not going to lose mechanical energy. The components of the mechanical energy are going to change. In other words, the size of the potential and kinetic energy is going to change along the path, but the sum is going to be the same. So as the ball goes down, the potential energy gets less and the kinetic energy gets more. But then as the ball moves up, the kinetic energy is going to get less and the potential energy more. But the mechanical energy at C is going to be the same as the mechanical energy at B and at A. So therefore we can say, if we look here now, this is number 4, I'm going here. So number 4, the mechanical energy at C is also going to equal the mechanical energy at B, which we know equals the mechanical energy at A, which is 102 joules. So let's now move to the next question, question 5. Question 5 asks us, what is the gravitational potential energy at sea? Well, we have that the height at sea is 3 meters, so we can work out the gravitational potential energy directly by using EP equals mgh. So we're going to do that. We're going to say, okay, so 5. I'm going to say 5. The potential energy at C is going to equal the mass of the ball times gravity times the height at C. And that's going to equal 2 kilograms times 9,8 newtons per kilogram times the height at C, which is 3 meters. So therefore the potential energy at C is going to equal, we use our calculators, so we're going to say 2 times 9,8 is 19.6 times 3, and that gives us 58,8 joules. So that is the potential energy at C, and we now can therefore use that to work out the kinetic energy at C, which is what question 6 is asking us. So we now go and we say, okay, so we know that the mechanical energy at C is equal to the potential energy at C plus the kinetic energy at C, and that must all equal 102 joules. Therefore, since the potential energy at C is 58,8 joules, when we add it to the kinetic energy, we should get an answer of 102 joules. So now we can work out the kinetic energy just by subtracting 58,8 joules from 102. We take it to the other side. So we're going to do that. And what we land up with is that the kinetic energy at C is 43,2 joules. And so by using conservation of mechanical energy, we have been able to solve this, what seemed to be a complex system. We've been able to simplify it by using conservation of mechanical energy. Let's now consider example 2. A ball is dropped from an unknown height. If it hits the ground at 12,52 meters per second, what is the height? Air friction can be ignored. So we are neglecting any effects due to air, so you can assume that this is being dropped in a vacuum. That immediately tells us that we can use conservation of mechanical energy, or the principle of the conservation of mechanical energy. Please note that the mass has been given to you in grams, so it's going to need to be converted to kilograms. And we have given you the velocity in meters per second, so this should actually be here, 12,52 meters per second. Seems to have moved from earlier. Right, so I'm going to leave this for you to do as a homework exercise, and then in the next video lesson I will provide you with the full solution to this problem.